2, 1. Okay, let's boogie. So arithmetic sequences. At some point in elementary school, you've gone through these sequences where possibly you were drawing little squares, stars, whatever, trees. And you noticed and you were trying to find a pattern between kind of the first term that they give you. So in this case, it's a 5. And then the second one, it's an 11. The third one is 17. Fourth one's 23. And it just continues on. And it creates a pattern for us. So we have this sequence, which is basically just a set of numbers that are following each other one after the other. Now, in arithmetic sequences, what you have is, the key thing is that between one term and another term, so 2 consecutive terms, there is always either an increase or a decrease, okay, within that number. So all arithmetic sequences either will increase continuously by the same amount from one term to another, or continuously decrease from one term to another. So in this case, I said a term. I'm going to start referring to these. So for instance, this is term 1. Okay, this would have been term 2. This would have been term 3. This would have been term 4. Okay, and it continues on, and we can find, a general term n, where n just stands for any number that we like. And that number is going to be some natural number, and we're starting from 1. So if you jump from one term to another, so if I would jump from here to here, I noticed that from 5 to 11, it has basically increased plus 6. And if I jump again between 2 consecutive terms, so let's say 11 to 17, again, I notice it jumps by 6. And this continues. So I've found a pattern. And this is one of the arithmetic sequences where the pattern is we're continuously increasing by some difference between the 2 terms that I have. So we can take any 2 terms. So for instance, if I take term 2 and term 1, I notice that my difference between them is going to be 6. And if I continue on, and if I take any term, n, and I subtract the previous one, so n minus 1, I'm still going to get 6. So no matter what I do, this is what I will have. Now, arithmetic sequences, most of the time for students, especially kind of in elementary school, if you start touching upon it, is that they just continuously increase. But this is not always the case. They can actually also decrease. So we could start with something and then it actually lowers, and it continuously lowers by the same amount. So the increase or the decrease from one term to another, I'll call a difference. Okay, so we can say that it's a difference d, for instance. Okay, so difference d, okay, so for these, it's always going to be the same. Now, our goal is going to try to find some kind of an expression or some kind of a formula for the general term in the sequence. So maybe it's term 10, maybe it's term 20, maybe it's term 300. So can we find a general sequence throughout? Now, one particular formula for these arithmetic sequences is called a recursive kind of formula or a recursive expression, where we can write and we know that, for instance, we can say that we have any term n that we like really is just the previous term. And in this case, all we're going to do to that previous term is we're going to be adding 6. Now, because we're trying to find our sequence, the general term n, from the previous one, so term n minus 1, we call this recursive because really we need to know the previous one in order to find, the current. Now, it's sometimes helpful, right, because we can build up. So if we know the first one, so if that first one would have been, let's say 5, and then it goes to 11, and then it goes to 17, and so on. So if we wanted to find term 2, right, really it's just take term 1 and add 6 to it, and you'll get 11. If you want to find term 3, take the second one, which is 11, and add 6 to it. Now, that works well as long as you know the previous term, right? So this recursive formula, it is useful, but recursive, okay? It is useful, but only if you know the previous one. Now, we have computers nowadays, so we can find these sequences pretty easily as long as we have these kind of formulas that we have. So I can use the recursive formula just fine. However, I don't want to be computing the previous ones on a continuous basis. So recursively just going over and over to trying to find it. What I would rather do is I would rather have some kind of a formula where I can say, well, if I want to know the 300th term, can I just figure it out right away? And for arithmetic sequences, you can. There's actually a very nice pattern as long as you know the difference between them. So the first thing that you have to do is you have to know, well, A, what is your first term? And then B, what is the difference between all the terms that you have? And if you have this information, you can actually find the general expression that you will have. So if I start within here, so what do I notice? That they're increasing continuously by 6. So if I would start from my first term, so let's say term number 1, I know that I'm going to be adding, so in this case I'm adding, okay? If I was trying to, if the sequence was actually decreasing, I would have been subtracting, but here I'm adding 6, right? So that's what I'm adding. Now that 6 really is just my difference. It's my general difference. So the difference is 6. I'm going to keep it at 6 for now. And now what happens? Well, if I wanted to know the second term, right, I would have just been taking that 6 and adding it to the first one. Okay. Now, if I wanted to know my third term, well, if I wanted to know my third term and I had my first term, then really it would have been 6 plus another 6. My fourth term would have been plus another 6. So what I'm doing is I'm really just taking that difference and I am just scaling it up, okay, continuously. And so if you notice, if I put this n, okay, if I multiply it by n, so what would happen? Let's see if this would have given me the correct answer. Okay, so actually I'll keep it like this. So if I want to know, so I would encourage you to do this. So if I want to know my second term, that would have been my first term plus 6. Okay, n is 2. Well, that's going to be 6 times 2, which is 12, plus 5, which is 17. So hold on a second. I just found my third term. So it can't be n, but what it can be is, it can be n minus 1. So in here, I can say, well, if it's n minus 1, so if I would do that, I would get my starting point. I know my difference. And now my second term, indeed, so 2 minus 1 is 1. So 5 plus 6 is going to be 11. And if I wanted to know my third term, I would have, okay, my initial term, the difference, okay, and that would have been 3 minus 1, which looks like, this is 17. So this seems to work. Now, does this actually work for all the arithmetic sequences? So the answer is yes, it definitely does work. So what we have is we kind of have our general formula that we can find any term that we like, as long as we know what the first term is and as long as we know the difference between the terms. Once you know that, okay, you're going to take the difference, you're going to multiply it by n minus 1, and then you'll have your result. So within us, or at least for our example that we have, this would have been 5 plus 6, okay? And then n minus 1. And in general, what we will do is that for any arithmetic sequence, you will take your first term, okay? This is going to be plus or minus whatever your difference is, okay? Depending if you're increasing or decreasing. And then you're going to be multiplying by n minus 1. And that is your general formula that you actually have, okay, in order to be able to find it. Sometimes what students do and sometimes what I do is, because I know the difference, okay, I can actually expand this out through. And so if you expand this out, we would get 5 plus, so 6, I'm going to distribute that in there, all right? So I would get something like this. Now I can collect my like terms, so this and this. So that would have given me 6n minus 1, and that is your general expression, okay, for our term. So 6n, because we're always continuously increasing by 6. And then the minus 1 is just because we want to make sure that we adjust it, okay, as we increase our sequence. So for these, this one and this one, okay, they're exactly identical, okay, if you wanted to know them. All right, so now that we have this, so does this mean, you know, I can take any arithmetic sequence and try to find what exactly happens to them, okay, over time? So let me give you a few examples, okay? So here's some other examples. So from what we said is, okay, if you notice that it is an arithmetic sequence, so either increasing or decreasing by the same amount, then we can find the general term, okay, the expression for it, relatively quickly. So let's take a look. So it's going from -9 to -4. So that would have been increasing by 5. And -4 to 1, it's increasing by 5. 1 to 6, increasing by 5. So all you do is you say, okay, so your any term that you like, so term n, right, is equal to whatever you start with. So whatever you start with. Now we're increasing, so this is going to be plus 5. That's your difference. And then it's going to be n minus 1. Now you can simplify this, of course. You can say, I'm going to put it up above there, -9, okay, plus 5n minus 5. You can collect that in there, which is going to be 5n, and then -9 minus the 5, which is going to be -14. And that can also give you the same type of expression. Now, there is something pretty neat here that you might notice. That when you write it in this form, okay, or, you know, as we wrote it within here, it kind of looks very similar to our equation of a line. Okay? Now, if you remember, the equation of a line was y is equal to mx plus b, where m was your slope and b was your y-intercept. And for sequences, although we can't really use x because x can be any value in between 0 and 1, you know, 1 and 2, and so on. So it's kind of continuous. But here we have discrete values, right? We have n is equal to 1, then it's equal to 2, then it's equal to 3, and so on. So it's not going to be exactly a line, but it's going to be a line which is made up of dots, okay? You know, and so on. So indeed, if you compare this, okay, so notice in here, it looks like, hey, wait a minute, 6n, so it's like x is my n, the slope is the 6, and then my y-intercept is this -1. And indeed, that is true. Because if you have the difference in between, that's kind of like, we call that the first difference when you were working with lines. That difference, that first difference, was identical and it was always equal to your slope. And this is exactly what we have. So in this example, when we say 5n minus 14, really it kind of means 5 is our slope. So it's increasing, okay, by 5. And it started off somewhere at -14. But that was at 0, remember, because it's the y-intercept. And for our sequences, really, we just start at 1. So it just kind of shifts over, and then the line is going to be in that direction. I'm going to actually plot one of these for you so that you can see it and how to do it on Desmos. And then you'll see that it's going to be just a regular line. Now, okay, for the next one, okay, so for this sequence, okay, so for this arithmetic, let's see if it's an arithmetic sequence. So this one looks like it's decreasing, okay, and it's decreasing by -10, -10, -10. So what does that mean? that means that the general expression for this is, again, you start with your original. Okay, that's term number 1. Now, in this case, we're decreasing, so it's going to be minus 10. And then it's still going to be n minus 1. So if you want to find any term, you can find it. So you want to term 100, you can plug in 100 in there, and you will get exactly what that term would be. Okay, now what about the last one? So often these sequences are just kind of made up of whole numbers. But that's not necessarily the case, right? I mean, you can have a sequence of numbers which are not increasing or decreasing by exactly a whole amount. So in this case, notice if I look at this and I start jumping around here, I'm going to go from 1.7 to 1.95. Well, so that looks like it's increased by 0.25. Okay, from here to here, it's also increased by 0.25. And here again, 0.25. So this pattern continues. So there is no difference here. Just because they're not whole numbers, you would still start, okay, with your first term. Now it's increasing, so it's going to be plus. It's increasing by 0.25, and we're going to say n minus 1. Okay, right there. And that's how you can find these general arithmetic expressions, even if they're going up or going down. Now, let me plot this for you in Desmos, just so that you can see that indeed it's going to be a line. Now, we're going to have, only points, because it's going to be 1, 2, 3, 4, because n, okay, is kind of the set of natural numbers within here. So maybe, we can define n. So for all of these, n, okay, is going to be equal to, okay, so 1. So it's going to be, I guess I should write this, okay, in terms of our, so it's almost like our domain, okay, that we have. So it belongs to 1, 2, 3, and so on. Okay, or you can write it as n, okay, belongs to the set of natural numbers. And that's just fine. And that's what we will have. Now, the range is also tricky, because remember, if you were doing, let's say, functions and you were talking about range, it was always in between certain things, because were working with continuous functions. But here it's discrete, so the range is actually going to be a set of points, right, that you have. So please keep that in mind. So now I'm going to bring out Desmos in here, and we're going to plot one of these out. All right, so here is Desmos. And now let's take a look and plot one of these. Let's maybe plot our original one that we had. Now, how do I plot this? Because I can't just say, for example, if I plot, what was it there for us? It was 5. Let's take a look here. 5 plus, 6. Okay, and then I guess I'm not going to call it n in here, so let's say if I put x minus 1, right? It's just going to plot a line for us. But that's not what we want. We don't really want a line. So how do we plot this? Well, I'm going to say, okay, so n is equal to, and this is how in Desmos you can write, okay, the list of elements. So we want it 1, and then we want this to continue. Let's, end it somewhere. I'm going to put it capital N, so it ends at some point. Sure, we'll put a slider in there, okay, and we'll end it at, let's say, 10. So we want 10 points, 1, 2, 3, 4, and we're going to plot it. Now, to plot this, so let's say if I plot it as a function, so f, okay, at x equals, so this was 5, and it was plus, so 6, n minus 1, okay. So this was, let me put this n, it's x, okay? So far this is what I see. Let me make this full. Now, I don't want this plotted, okay? What I do want is I want it plotted only at the points 1, 2, 3, 4, well, in this case up to 10. So the way to do that is you're going to create kind of like a table of values, okay? So for every n, I'm going to do this. I'm going to be substituting n in there. Okay. And so now if I scale this back, you'll notice that it's going to start creating a nice line. So what I plotted in there, notice the n, it's taking from, because I'm defining it as 1, 2. So for n equals to 1, okay, it substitutes into my function f1, and it will get whatever result it is there. And then I will continue with that. Now, if I plotted this, okay, notice what will happen. Okay, it's going to do that. And I'm just going to show you, okay, because I want to show you the y-intercept. Notice it's -1, right? And that is coming from, so if we go back in here, okay, when we simplified it right there, we got 6n minus 1. And indeed, the slope is 6, okay, and the y-intercept is -1. So these arithmetic sequences are basically lines. And if they're increasing, it's going to be a straight line up. And if they're decreasing, it's going to be a straight line down. It's going to start somewhere and go down. All right? So that's how you can actually plot these for yourself. And this is how you can actually find the general term in the sequence. Now, what if, I have a couple of examples here for you. So here's an example. What if you weren't given a sequence? What if you were just told, let's say, that you have an arithmetic sequence, right? So I'm telling you, you have an arithmetic sequence, and within that sequence, you know the 12th term was 56, and you know that the 21st term was 12. And now what if they say find the general Tn formula, or the Tn expression? Well, you would say, well, that's interesting. Tn is supposed to be equal to my term 1, you know, plus or minus whatever it is increasing or decreasing by. Okay, that's d. And then I'm going to be multiplying it by n minus 1. Okay, so that's nice. But now, I don't know d. Because I don't have a sequence, right? I can't actually check. Now, they told me that it's an arithmetic sequence. So how would I figure this out? Because I don't know my first term and I don't really know the difference. Well, but hold on a second. So think back. If you know that arithmetic sequences are lines, right? They're going to be either increasing or they're going to be decreasing, depending on what the slope is, right? So there's some kind of lines. Now, they're, of course, lines made up of points and not exactly lines. So they're like this. So if we know it's a line and we have an equation of a line, well, then we have 2 points. We have 12, okay, and the result is 56. So we basically have 12, and that gives me 56. And I know 21, the 21st term, and that gives me 12. So it looks like it's going to be decreasing, right? So it's a decreasing sequence. But I have two points. If I have 2 points, then I can find the slope. But the slope is just the difference, right? That's what that is. So if I know the difference now, then I can basically create an equation of the line. And then I can find my y-intercept. And I'm done. So I can actually find it from there. So let's do that. So recall. So you can now use your stuff that you've learned about lines. So the slope, well, what was the slope? The slope was rise over run, right? So let's say, you know, y2 minus y1 divided by x2 minus x1. So this is nothing else but rise over run. That's what we have there. Well, I know what that is. So you can pick, okay? So let's make this point, you know, point number 2, and this point number 1. So what I have is, so I'm going to have 12 minus 56 divided by, and this is going to be x2, which is 21 minus 12. So that's going to give me some number, right? So 12 minus 56, so it's going to be negative. So 56, 46, 44 divided by, and now 21 minus 12, so that's going to be what, 9. Okay, So that's my slope. Not very pretty, but nobody said it would have to be. So we have negative 44 over 9. That would have been my slope. That's the same thing as your difference, right? So remember, that's what that would be. That's the difference within. So now if I know my difference, okay, and again, I'm going to kind of write it as a line, y is equal to mx plus b. So I have m, which is negative 44 over 9, okay? This x, really what this x is, okay, that's your n, okay? That's your n. Your slope, okay, we know. The y-intercept we still don't know. And then this y really is just Tn. Okay, so that's your n, whatever we have. But we have a point. So to find the y-intercept, you can find that, no problem. You can just take one of the points. So let's say take point number 2. So it's going to be 12 equals negative 44 over 9. This was, okay, the 21st. And now I can literally solve for b. So whatever b will be right there. Okay? So, well, let's do it. So I'm going to, it's kind of annoying because the numbers aren't very pretty. Let's see. Well, 9. Okay, notice I can reduce that. So by 3. Okay, this is going to be 7. I can't reduce it any further. So that's fine. This is going to be 12. So let me just compute for b. Okay, I'll do it in fast forward fashion just to find it. I think you get the gist. Okay, so here's your b. So now we know exactly what the expression would be. Okay, so our general expression, so for this, let me make this a little bit smaller, put it on the side. So what we have is Tn is equal to negative 44 over 9n plus 3 44 over 3. So I kept it as fractions, which is fine. And now let me just plot this. I'm going to plot it on Desmos, okay, as a sequence. And then we'll see, you know, if we do get these, where basically it says here the 12th term is 56 and the 21st term is supposed to be 12. And now it's asking us for the 40th term. So we can substitute 40 into here and we can get what that answer would be. Or I can get it off of the graph as well. Okay, so let me plot it on Desmos. And so I'm going to do that. I'm going to take out the Desmos within here. Okay, let's put it there. Now, since I have these, so we're going to go first. Let's go to, this was what, the 12th term. Okay, and so we'll try to do that. That's the 12th term. Let's change this up. Okay, so we have f of x, which is going to be negative 44 over 9. Okay, x plus, it's going to be 344 over 3. So this is what we have. And so notice, here's our line. Okay, and our points. I'm going to remove that line. Okay, so notice here's our 12th term, which was 56. Okay, now if I wanted, which was the other one, which was the 21st term. So I'm going to do that, 21st. Okay, let's see. So that sequence, again, it goes down. There we have it. Okay, notice it's 12. Now, if I wanted to get it up to 40, of course, I can substitute it in and get exactly what that would be. But, you know, I'm going to just show you visually what happens. Okay, so it gets down all the way, okay, to there. So it's about negative 80.889. So, I mean, it's going to be some kind of a fraction that we would have if we plugged it in. So this was a great question. So even if you don't know the pattern, as long as you have two terms in this sequence, because you know that arithmetic sequences are just really just kind of like lines, because their first difference is the same, then you can create and find the general expression if you ever needed to. So this was a great question that you have. All right. Okay, so I'm going to end the video here. And I think this is going to be hopefully useful for some of you starting off with these arithmetic sequences. And I also showed you on how you can actually plot this in Desmos. So any sequence that you want, you should be able to construct the general expression for it. All right. All right. Thanks for watching. We'll see you in a future video. Bye, everybody.